Okay. I'll even turn on the projector. But what I was saying, my office hours this week are a little strange, stranger than normal. On tomorrow, normally I have office hours from 9:45 until 11:30 in the morning. That's the only office hours I have on Tuesday and Thursday. Well, tomorrow, because I'm taking my afternoon class on a field trip, I have to pick up the van from the Birmingham campus, and the only time I can get it, because I have a 8:30 class here, I can't get it at 8 in the morning over there, because there wouldn't be time to get here for my 8:30 class. So I'm going to have to go at 9:45 to pick up the van and come back here. So there's most of my office hours are shot. I'll be here before 11:30, but I don't know what time before 11:30. So there's that one. Then on Thursday, I'm giving that class, that mini-term class, its final exam, and we'll be through early. So I'm probably going to leave a little early on Thursday, just because I normally don't have office hours then. My office hours are 9:45 until 11:30, so that's nothing new. I'll be here then, but on the latter part of the day, usually I'm back in the office 5:45 to 6. I'm not going to be here that late on Thursday because we got to leave and go to Georgia. So therefore, the point of that story is my office hours on Friday are completely gone. I'll be on taking leave that day, personal leave, so I'll be over at Georgia. So don't look for me Friday on the Birmingham campus or on this campus. I won't be on either one. All right, now this I didn't announce them before because Bill was the only one in here, but there's Scholarship Summit coming up Wednesday and Thursday. Now, I don't know where y'all are in your things. Are you planning to graduate? Do you have plans to transfer to a university or unsure how to pay for the remainder of your education? Come educate yourself on the college transfer process and transfer scholarship opportunities available from some of the leading colleges in the state. And this will be Wednesday, October the 9th at the Academic Success Center. That's that new building on the Birmingham West campus. It's right across the street, Wilson Road from the East campus. And that's in their auditorium, the Academic Success Center Auditorium, Birmingham campus, 1 to 3 o'clock in the afternoon. Then Thursday on this campus, in the faculty staff dining room, which is right next to the cafeteria, and that will be again from 1 to 3 o'clock Thursday afternoon. The Scholarship Summit Fall 2019 participants include Alabama A&M, Alabama State, UAH, Birmingham Southern, Jacksonville State, Tuskegee, Miles, University of Alabama Tuscaloosa, University of Alabama Birmingham, Mercer University from over in Georgia, Samford University from Birmingham Homewood, University of West Alabama, University of North Alabama, Mississippi State University, and University of South Alabama. So all over the place. They will be here for both of those days. All right. And then the NCAS, NASA's Community College Aerospace Scholars Program will be accepting applicants through October 16th. That's just a little over a week away. So if you're interested in participating, get the applications in. I'll give you this information, websites, all that kind of stuff. You can follow up on that. Okay. Sorry that took longer than I intended, but thought y'all needed to hear it in case any of you are interested. All right, we're in Chapter 2, First Order Differential Equations, 2.4 Exact Equations, and we were talking about how to make a non-exact differential equation exact. And that's where we left off. First, any questions on anything we've done so far? All right, and again, get me something by next Wednesday, either your research paper, your first test, or both. Okay. Now, we were on example 4, and I'm going to write down parts of example 4. Let me get my pen set up. Okay. Okay. xy dx, pretty simple m function, plus 2x squared plus 3y squared minus 20 dy equals 0. Now, it certainly has the setup that you want to investigate to see if it could be an exact differential equation. But when you do the test, you find out it's not. Take the partial of m with respect to y, and you get x. Take the partial of n with respect to x, and you get 4x. Okay? Not the same. But they're not that far apart, and we did the found our integrating factor, which was y cubed, and that's where we left off. And so let's take our integrating factor and multiply it by everything. So our, what did they call it, mu, was it? Yeah, mu of y is equal to y cubed. We found that last time, okay? So we multiply that by everything. X y to the fourth dx plus, now you have to multiply every term by it, 2x squared y cubed plus 3y to the fifth minus 20 y cubed dy is still equal to 0, because 0 times y cubed is still 0. All right? Still need to verify that this is exact now. Is it? What's the test? You do the partial of x, y fourth with respect to y. Why not? Okay, and what does that give us? Okay. And we also do the partial of that mess. I'm going to write it all down again with respect to x. And what does that give us? 4xy cubed. And then that with respect to x is 0. That with respect to x. Hey! Yes, we have them. Okay? We better, because we did the work to get there. So, we know we can do it. Now we get to going about doing it. Now, I'm going to erase this because I just have a sneaking suspicion I'll need all the room I can get. Okay? So, what's your first step? And you can do them in any order you want to. What have you got to do? What is your assumption here? You have some function, f of x, y, that is a constant, right? Yeah, is equal to a constant, equals c. Okay? And that, now which way you want to do first? Want to do the partial of that with respect to x and do this one, or with respect to y and do that one? Don't have to do them both at some point, which way you want to do it. Matter to you? What you think? It makes a big difference, does it? Yeah or nay? Okay. Let's just do partial of this f, which we don't know what it is yet, with respect to x. That had better be x, y to the fourth. Because if this is your solution to that, then the partial of f with respect to x had better be this term here. Okay? So let's go with that. Right, in differential form, it's a dx. Okay, and this would just be f is equal to, when you integrate that with respect to x, what do you get? x squared over 2 y to the 4th, okay, plus some possible, not constant, g of y. Okay, some possible g of y. Okay? Okay, we got that. Now, with that in place, if you take the partial of that f, that's the same f now, that's the f of xy, okay, and take the partial of that with respect to y, you should get this thing over here, right? So let's do it. The partial of f with respect to y would then be, take the partial of that with respect to y. 2x squared. Third, is that what you said? Plus g prime of y. And that had better be equal to this thing here. 2x squared y cubed. Hey, that's looking good. Plus 3 y to the 5th minus 20. Oh, yeah, y cubed. Okay. Well, since these two are exactly the same, you can subtract those off, and that gives you dg dy is equal to 3y to the 5th minus 20 y cubed. And what can you do here? Yep. First, write it as a differential, and then integrate. And you get your g of y is equal to 1/2 y to the 6th 5 y to the 4th. Okay, that's your g of y. So plug that back in here. So this f of xy is going to be x squared y to the 4th over 2 plus y to the 6th over 2 minus 5 y to the 4th. That's your f of xy. Equals c. Okay, that's your solution. Not the f, but that it's equal to c. Okay? Now, I don't think this was a boundary value problem, so let's see what they got. 1/2 x squared y 4th, yes. Plus 1/2 y 6th, yes. Minus 5x 4th equals c, yes, you've got it. Done. Whoa, and that was the last example in section 2.4. They have some remarks then at the top of the next page. And they just talk about some texts doing things in different order and what your p of x could be for a linear equation and that kind of stuff. We kind of hit on that a little bit before, but it's not worth focusing too much attention or effort on, I don't think, unless you want to pursue something in the remarks. So homework exercise is almost exactly what I gave you before. Any of the odds 1 through 19 that are in the back of the book, any of the odds 21 through 25 that are in the back of the book, 27 if it's in the back, 29 if it's in the back, any of the odds 31 to 35 if they're in the back, and 37 if it's in the back, 39 if it's in the back. Now, most of the time, the discussion problems are not in the back, but if you find some that are, you can do any of those odds as well. There's a mathematical model here, a falling chain, which is an interesting little practice. If we had time, I'd go into how I saw that model actually lived out in living color when I was in the Navy, but there's not time for that story, so sorry about that. Computer lab assignments, if you have a computer lab at your convenience, disposal, then by all means you can take a look at that one problem for a computer lab, which is streamlines. And if you're into aerospace engineering, probably some of mechanical engineering, you could easily get into some product design that you would be using streamlines to look at things like airflow and that type of thing. So that may be of interest to you if you're in those areas. Section 2.5 is solutions by substitution. Okay? And let me clear the screen. Say here, usually solve a differential equation by recognizing it as a certain kind of equation. That is, like we've been talking about, is it separable? Is it linear? Is it exact? And so on. And then carrying out a procedure consisting of equation-specific mathematical steps, okay? Separating the variables and integrating, multiplying through by integrating factor, blah, blah, blah. Doing your test, whatever. Often the first step in solving a differential equation consists of transforming it into another differential equation by means of a substitution. That sort of sounds a little bit like your good old U substitution in calculus, what was that, end of 1, beginning of 2, somewhere around there. For example, suppose we wish to transform the first order differential equation dy dx equal f of xy by substitution that y is equal to g of xu, and u is regarded as a function of x alone. If g possesses first partial derivatives, then by the chain rule, okay, now this is another one of these blah, blah, blahs at the beginning. So let's see if we can follow what they're saying. Here is her differential equation. Dy dx is equal to some function of x and y. And let's say that it doesn't look like it's going to be separable, easily separable. You try doing linear, and it doesn't fit the bill there. You look at exact, and it doesn't look like it's very exact, and maybe even try a integrating factor with the exact like we just did. Nothing seems to be working, okay? So what they suggest here is that you first do a substitute and do y is equal to some g of ux. Is that right? xu. Okay, I thought it usually put x first, but just thought in my mind it said a u first. But okay, xu. I can't write x anything without wanting to write it as a y. Okay, xu. Especially since u starts off being a lot like a y does. Okay. Now, where u is some function of y alone. Okay. Now, no, something's wrong with that picture there. No, a variable x alone. Okay. I was going to say that isn't making any sense whatsoever. Okay. So u is a function of x alone. Now somehow to me something seems a little fishy here, because y is a function of x and u, but u is a function of x alone, so it seems like y should be a function of x alone. Okay? And maybe it is. Okay? But f is a function of x and y. So again, they start muddying the water here. Okay? Now, if g possesses first partial derivatives, then the chain rule is appropriate. So your dy dx is what we're looking for anyway. is equal to the, I'm real tempted to write it this, yeah, I am going to write it that way. The partial of g with respect to x times the dx plus the partial of g with respect to u du dx. Remember, u is a function of x alone. Okay? That's just by definition. If y is a function of g and x, then you can take partials. If that g has partial derivatives, you can take them this way. Of course, dx is 1, right? Okay. Now, so that gives us, it's saying the same thing, so I'm just going to write it here. G sub x, that's the partial g with respect to x, plus g sub u prime. Okay? It's just writing a little more shorthandedly. In fact, maybe a bit too shorthandedly. They say du dx, but the prime is with respect to x. Okay? And both of those partials of g are functions of x and u. I didn't write that in. Yeah. If we replace this dy dx here with that, okay, what we get is this thing, which is our dy dx, which is g sub x plus g sub y du dx is equal to your f of x, comma, g of xu. Did it again. I cannot write a u without making it look like a y. U, okay. Now what we've done, we've replaced this with this, or this actually, okay? And then on this side, we've placed f of g of the y is, f of x, and then the y is g of xu. Okay. Now, if you solve this for your du dx, for right here, then what you would do is subtract the g sub x from both sides, and then divide by g sub y. Okay, that's partial g with respect to y. So that goes out, and you get du dx is equal to this mess on top here. Sorry about that. F of x, g of xu minus g sub x, that's the function of x and u, over g sub y, which is also a function of x and u. Okay. Now, this on the right-hand side is lots of mess there. And they say, let's just let that be some big function, capital F, of x and u. Now this is where they start monkeying around, changing names so many times it's almost hard to keep up. And what they do next, if we can determine a solution that u is some phi of x. Now why introduce all these new things? But let's say there is a solution, u is equal phi of x of that last equation. Then a solution to the original equation is y is equal to that function g of x phi of x. Okay? Because that's what your u was. Okay? All right. In the discussion that follows, we examine three different kinds of first-order differential equations that are solvable by means of a substitution. So they just leave this hanging right there, and we'll look at the things. Hopefully you'll be able to go back and see how it might tie together, or not. Okay, so let's first look at homogeneous. Now wait a minute, or homogeneous. Thought we had these before, and I think I told you at the time, sure, we're calling these homogeneous equations, but then we're going to have another homogeneous equation that has nothing to do with the earlier ones, okay? And here's what we mean by homogeneous equation here, okay? If a function f, this is new topic here, if a function f possesses this property, that you have f of tx, ty equals some t to the alpha times f of xy, and that's pretty ugly, isn't it? Okay, t to the alpha f of xy. If it has that property, then we, for some real number a, alpha, and that's a real number, no imaginary numbers, could be, irrational, whatever. If that's true for some rational a, then, real number a, we say f is a homogeneous function. Okay, homogeneous function of degree alpha. Okay, now, here's their example, and I hope you see it's easier than they make it out to be. Okay? That is a big, wordy, definition. Here's an example. F of xy is equal to x cubed plus y cubed. Okay? That's a pretty simple one, but that's an homogeneous equation of degree 3. So let me tell you what I consider my shorthand for doing this. Rather than thinking of t's in there and alphas and stuff like that, just look at the degree of each term. If the degree of each term is the same, then that's an homogeneous equation of that degree. If they're not, it's not an homogeneous equation. Okay? Now that one's pretty obvious, that it is. But they're going to show how they go about doing it. Remember, let's now consider some f of tx, ty we've multiplied the independent variable, each of the independent variables by t. So you do to the first one, you cube it, that would be t cubed x cubed, and to the second one you cube it, and that would be plus t cubed y cubed. And what you can do, factor out a t cubed, and then you have x cubed plus y cubed. And this indicates, and this is t cubed f of xy, because that was your alpha of xy was x cubed plus y cubed. So t cubed. So your alpha, degree of this homogeneous equation, is 3. Okay. That is a lot of blah, blah, blah to say all the terms have the same degree. And that's the degree of your homogeneous equation. Okay? How about this one? F of xy is equal to x cubed plus y cubed plus 1. Is that homogeneous? No, that third term is not the same degree as the first two. So even though it's almost the same equation, it's not homogeneous. The first one is. Okay? So don't let extra little term in there throw you off. Okay. All right. So what if we have, looking like you're exact, but it doesn't have to be, m of xy dx plus n of xy dy equal 0. Okay? I've lost it. There it is. Okay. It's said to be homogeneous if m of xy and n of xy are both homogeneous that's a pretty ugly writing of homogeneous, of same degree. N, I guess it is. I just threw the N in there. Okay. And you can go through and do the T's if you want to, but just look at them and see if all the terms in both the M and the N are of the same degree. That's what you're looking at. Now, if they are homogeneous functions of degree alpha, then you can also write this. M of xy is equal x to the alpha times m sub 1 alpha. No, I'm sorry, they don't use alpha. I didn't mean to put alpha. Bring up a new variable, why not? U, okay. Now, where did that come from, okay? But remember, your x's and y's are of the same degree. So basically, here's what you've done to make that happen. It seems like magic, but that's not necessarily what it is. But you can also say, before I get to what you did there, so I'll get it all down, I don't want to forget the other part of this, that the n of xy is equal to x to the alpha times n. Of 1u. Okay. Now, where did the u come from? U is 1 over x. Okay. Now, and again, y. Okay. Remember, both of these are of degree alpha. So if you pull out, factor out an alpha, x to the alpha, yeah, your x basically goes to 1, and seems like maybe it should be y, but no, I'm sorry. U is y over x. I knew I wrote something down. U is y over x. Okay. Now my screen changes. Okay, yeah. Now that makes more sense. You factor out the x to the alpha because everything has that in it. Has some degree alpha. Factor out x to the alpha. And that leaves you, your x variable is 1, and your y is y over x to the alpha. Okay? So then, but y has to be, summation of all the terms have to be alpha as well. So then your u then becomes this, the y over x. Okay, that's a real quick and dirty explanation of what they're doing, if you can buy that. Okay? But you could have also done it the other way, and I'm going to erase some stuff up here. All right, take care. See you Wednesday. Okay. All right. We don't need these anymore. I wish I'd have erased them earlier. Whoops. Yeah. Because I needed the room. I thought, hey, it looks like we got enough down here. Yeah, right. Okay. Or on the other hand, depending on how many hands you've got, you could say that m of xy is equal to, this time they factor out a y to the alpha, and then you have m to the, I think you use v this time, don't we? Yeah, v1, okay? Okay? Same type deal, you divide it out, a y to the alpha, that leaves your y variable just be 1, and your v to be, and by the way, also let me go and put this in, n of xy is equal to y to the alpha times n of v. Yuck. This pen is so slow when I get this much writing on it that I can't, it doesn't write as fast as I do, and then if I pause, I don't know where to put the next one, v1, where v is equal to x over y. Okay, so you see there's a certain kind of a symmetry to this. All right, now let's rewrite this as y is equal to ux, and rewrite this one as x is equal to v. Yuck. Okay. Okay. V times y. Y is equal to ux. X is equal to vy. Okay. So those are new dependent variables. We'll reduce the homogeneous equation to a separable first-order differential equation. Yes, I think I can go for that. Okay. Okay, I did bring my watch up, but I haven't put it on the desk yet. So, all right. Okay. What's that? Yeah, we only got a 5-minute jump start, so it's 3:40. Yeah, we got plenty of time. Yeah, and he left. He said around 3, and I guess it was pretty close to that. Okay. Now, here's what we would be doing if this was the original differential equation, and let's just say it wasn't exact, and you couldn't make it become exact, but it was homogeneous, okay? Then let's factor out and do what it said here. Your m sub x, y, we're going to write it as x to the alpha m sub 1 u plus dx plus x to the alpha n sub 1 u dy is equal to 0. Okay? That's one way you could write it. Or you could write y to the alpha m sub m of v1 dx plus y to the alpha n of v1 dy plus okay, let's just leave it like that for now. That's equal to 0.
My internet book
Yeah.
does not put the y to the alpha.
Okay. You're absolutely right. They don't, do they? Not in the paper black copy either. I had not noticed that. I just do it because it belongs there.
And they didn't use the V, or they used it up top.
No, okay.
Unless I'm looking in the wrong spot.
Wait. Oh, wait. I'm sorry. I was jumping the gun. I was just saying that's another way you could do it. Sorry, I'm off. I'm glad you caught that. You could have done that, but we're not.
That way it makes sense, too. Because it's just...
Yeah. I just erased more than I intended to, but let's see if we can get them back. Okay, this was the y. Okay. All right. So, no, what they do, they divide out the x of alpha. I'm sorry, I was jumping ahead. If you divide both sides by x of alpha. Now, this is, of course, assuming x of alpha can't be 0. But I think you need to assume that anyway. And then this gives you m sub 1u dx plus n sub 1u dy is equal to 0. Now, let's go back and remember that your u is your y over x, okay? Or y is equal to u times x, okay? Whichever of those you happen to choose, let's see, which way? Then, let's do down here, let's carry that out to what we need it to be. dy is equal to u dx plus x du dx. Okay. I'm sorry that's all messed up in there. Again, my pen's not writing fast enough, so I can't see where I'm doing this. This came from y is equal to ux. Okay. When we did a dy there, that's what we get. Okay. Now, if you look at that another way, just leaving out the dy's, I mean the dx's and the denominators anyway, you have dy is equal to u dx plus x du. I'm sorry, I did it again. I can't get my pen back. Goodness gracious. Okay. Every time I want, not every time, but most of the time when I do a du, it comes out of dy. I can't get the pen back. Come on back. There we go. Okay. du. Okay. If you look at that, that's what it turns out to be. The dy is simply a exact differential u dx plus x du. Okay. Now, there's a real temptation to stop and integrate there, but that's not probably the best move here. Okay. All right. They say the last equation, and I'm trying to find the last equation. I guess that's the one up here. And you put, instead of dy, you put this. So let's see if that will work. M of 1 u dx plus n of 1 u. Instead of dy, we write that as u dx plus x du. Okay. Now let's sort of combine things together that need to go together. This will be m of 1 u dx plus n of 1 u. I'll put the u here in front, dx plus, I'll put the n and x in front. Now, goodness gracious, this is so aggravating. X times n of 1 u du. All right. At this point, get our dx's together and our du's together. Yeah. And here's what we got. M of 1 u plus u. I made it a mu, didn't I? Yuck. Okay, that's the u. N of 1 u dx plus x n of 1 u du is equal to 0. Okay. Now at this point, I think I need to erase. I hope I don't need it for anything else. Let me erase some of these lines down here. I know I've already used them, but it still feels like I might need them again. And my pen is not erasing good well at all. Okay. All right, so what do we have here? They go through all this mess and then tell you, now don't use this formula. Do the procedure. Don't use the formula. But let's see what we've got now. If I haven't erased too much here, please tell me I didn't erase the wrong stuff. Yeah, I think that's all right. You see, these are all functions of u, and this is the only function of x. So what we have, if we divide both sides by x, and divide everything else by your this expression of u here. So here's what you would get. Dx over x, that's all that would be left here, plus, and you divided this out, and you have n of 1 u. Alright. Man. Alright, that's n of 1 u. I think I'm going to get rid of this just because it's totally in the way. And we divided it all out anyway, so. Alright. And divide that by m of 1 u plus u. Did it again. U, not a mu. Okay. Yeah. All right. Still trying to find it. U and this thing, my pen has quit writing. Okay, there we go. U n of 1 u dy, okay, is equal to 0. Notice This is all a function of x. This is all a function of u. Oh, that's not a du, that's dy, that's a du. I did it again. Okay, that's du. It's a du down here, it's a du up here. And this is all a function of u, so sure enough we have the separation of variable problem. Okay? At this point we offer the same advice in preceding sections. Do not memorize anything here, especially the last formula. Rather work through the procedure each time and the proof of the substitution, the proof that the substitution y is equal to vi, x is equal to vy, and dx equal to v dy and plus y dv also lead to separable equations, but then it'll be v and y, not x and u. Okay, so, yeah.
Why don't you just go on integrate this thing to an integrating factor?
Right.
I mean, why don't you just go and do that rather than say, okay, let's stop here and just go around and figure it out from there?
I can't quite answer the question because I haven't figured out why they go through all this rigmarole and then say, but don't memorize this, just do this. You know, why don't they just say, forget about this, do this? You know, and that would be.
Just go straight to an example.
Yeah.
I can hardly follow this.
Yeah. The point of this is showing that it does get it in the separation of the variables.
Yes.
Then we're going to turn around and see how to do it without introducing new variables and things like this. Like you say, just using a integrating factor.
Yeah, but I'm saying why he just didn't do it right here.
I know.
Just put an integrating factor and say, now that's one step. Let's try from here.
Yeah,
Blah, blah,
and see
blah.
if it works, and if it does, we'll use it. You know, if a trick works more than once, call it a method. Yeah, I'm all in favor of that.
I mean, you introduced a lot of stuff, and then
Yeah, and
it
it's
doesn't matter. Don't worry about it.
yeah,
Just follow the procedure.
and I don't know. It's
That's fine.
yeah, but let's see if there's
That's what he said.
an easier way to do it.
That's not what I said.
We got all the stuff down. Let's see if what we can do with it. Here is the example one. Do we have time? Yeah, I think so. I hope so. X squared plus y squared dx plus x squared minus xy dy is equal to 0. All right. Now, I think as Bill's already alluding to, let's see what we got here. Number one is homogeneous. Every term in both of those functions, x squared, y squared, xy, they all are degree 2. Every one of those is degree 2. So it is homogeneous. Okay. Now, they're all homogeneous functions of degree 2. Now, they are suggesting that we use y is equal to ux. Okay? Now, good choice there. You could have used x equal vy. But let's just see what happens with this one. If you got that, then change this to dy is equal to u dx plus x du. Okay. All right. Now, substituting that in for dy only and the y, both y and dy. So this will be x squared plus, that would be u squared x squared, right? dx plus, and this will be x squared minus x squared u. Don't really care which way you do it. You got two x's and a u, okay? X squared u dy, oops, we have to substitute that too. Okay, and here we do a u dx plus x du. Okay, now, just a little note here. Sure doesn't look homogeneous anymore, does it? Okay, and it's not, or it doesn't, at least it sure doesn't seem to be. But that's okay. It doesn't have to stay homogeneous. This is x squared plus u squared x squared dx plus, and now let's multiply through, and kind of foiling these things, okay? X squared u minus x squared u squared, these are all times your dx here, plus x cubed minus x cubed u du. All right, I hope I did that right. Okay. Now, what we're going to do is factor out the x squared here. 1 plus u squared dx. Okay? And, oops. We got more dx's here. Let me get these in on the picture too. Okay. And they all have x squareds in front of them. We're adding these two together. So that will be plus u, factor out the x squared, minus, factor out the x squared, u squared. I wrote a mu again, I swear. I say u and write mu, I say u and write y, I don't know. U squared. Okay. When we got all those together, I sure hope I did them right, it looks like these two disappear. Right? And that's times your dx plus, factor out the x cubed here, you have 1 minus u du. And all this I left out here is equal to 0, is equal to 0, is equal to 0. All right. Now we see they're separable. Okay? So here we have an x squared over x cubed, which is just 1 over x. Okay? Dx plus, and we got rid of that, and we have 1 minus u over 1 plus u du is equal to 0. Okay? And sure enough, at this point, we can integrate both sides. Now, not quite, but close. What do we need to do to that? Second?
That should be of x. Wait, no.
No. Right. So what we need to do is long division of that. We come over here and do 1 plus u into 1 minus u. Actually, I like to do long division the other way, so let me always write it in descending order of power. Okay? What's that?
I never learned how to do long division
With polynomials?
Sure.
Oh, okay. It's about time, huh? Okay. What you do is the denominator into the numerator, so it make this a u plus 1 into a minus u plus 1. Okay? Well, just like with numbers, adding, subtracting, and multiplying we usually do right to left. Division you do left to right. So u into minus u would give you a minus 1. Then you multiply. Minus 1 times u is minus u. Minus 1 times 1 is minus 1. Then you subtract, but with signed numbers, I like to change signs and add. So let's do that. Add these, that goes to 0, and you have 2. Well, that's a remainder, so put plus 2 over u plus 1. All right.
So you change signs why now?
Second?
You change the signs.
Well, when you subtract, after you multiply, you subtract. I'll do change signs and add. It just keeps me from making sign errors, S-I-G-N errors. Okay, so let's rewrite this as 1 over x dx plus, in parentheses, a minus 1 plus 2 over u plus 1 du is equal to 0. Okay, now we can integrate each term. Okay, this is what? ln of x plus, okay, actually it'll start off being, now do each of these separately, okay. Let's first do the integral of, oh, that's not what I want. Okay, that's what I want. That would be a minus u, right? Okay. Plus, what would the next one be? 2 times ln of u plus 1. Okay? And that's equal to some constant c. Okay? Now this will be ln of x minus u plus ln of u plus 1 squared. I don't have to have absolute values anymore, is equal to c. Okay? Now, everything would be all right with the world except we got u's in there, and our original problem had y's. So let's go back and put what u is, or u are, and u is equal to y over x. I think they do this, don't they? Yeah. So let's do that. That's our final answer down here. So this will be the ln of x. I probably should have absolute values on that too, but let's just not for a bit. Minus y over x plus ln of, now u is y over x, so this will be y plus x squared, over x, okay, squared, okay. I think I did that right. That would be y over x plus x over x, this would be 1, okay, and that would be that squared, and this is equal to c. All right. Now, and actually, they did a log C, and they didn't do what I did, but let's go on and see it. Yeah, we're going to get there, okay. They did a log C, not a C, because they have 2 logs over there. All right. So let's take all those, okay, let's get this on one side. Y over x is equal to log x plus log of y plus x over x squared. And let's just make this plus a log c. I know it doesn't matter. It's just some constant. Okay, so let's get all these things. Y over x is equal to the log of, okay, we're going to multiply these things together. So it's going to have a c, right? Because the log of the sum is the sum of logs is the log of a product, right? The log of a product is the sum of logs. Y'all never use phi rule, so you didn't know that, but that's one of the rules of logarithms. So this is going to be cx times y plus x squared over x squared, which is just going to make a x here and lose that x there. Okay. All right. Now, believe it or not, no, they put the c downstairs with the x. And it's, you know, it wouldn't matter. You could have made this log 1 over c there, and it would have been downstairs. So they put it down here with the x. Okay. Now, at this point, they e both sides. Okay? Huh?
You're always eating something.
Yeah, we're going to eat something here, and let's eat it and see what we get. E to the y over x is equal to y plus x squared over cx. Okay? Now, multiply by your cx, and you have y, they put it x plus y, it doesn't matter. X plus y squared is equal to cx e to the y over x. Okay? It's ugly, but that's what it does. And that's their answer. Okay? So, Bill, I'm in complete agreement with you. If you have a homogeneous equation, why go through all that mess except showing you it does become separable variables? I guess that's why they did it. But then, if you have homogeneous, then pick. And you can choose either one of them you want to. And if one doesn't work, try the other one. U is equal to y over x, or v is equal to x over y, and the corresponding pieces there. See it and see if you can get separation of variables. Use tricks along the way to get you where you need to be, but that's solving a homogeneous differential equation when you're talking about that being all of the terms have the same degree. Okay. I think we're out of, in fact, we went to almost our regular time, didn't we?
Yeah.
We'll start next time with Bernoulli's equation.
Yeah, I'll just do it the other way we've been doing it.
Now,
It seems easier.
if you don't know who Bernoulli is, that may be because there were a lot of different Bernoullis. Okay, there was two brothers, Johann and Jacques, or something like that. Brilliant mathematicians and physicists too, and I think the younger one thought he was smarter than the older one, or vice versa. I don't know. They sort of fought like cats and dogs, competed with each other. Maybe that's what kept them both pretty bright. I don't know. But anyway, they were near top of the field in anything. And I know one of them had at least one son, but there was another one in there too. I don't know if it was the other one's son or one had two sons or whatever. In the next generation, Daniel Bernoulli turned out being very, very bright too. And there was some competition going on that just about one of the two brothers almost always won. And this one thought he had it until he found out the results, saw Bernoulli had won. He thought it was himself until he realized it was his son that won this time, not his brother. He kicked him out of the house. So they continue fighting like cats and dogs. I think there was another one in there too. One went more toward physics or something, but just a family full of geniuses. This is a Bernoulli's equation that came out of one of those Bernoullis, and I don't know which one it was. But we'll do Bernoulli's equation next time. That's where we'll start. Homework exercises here. I think you can do any of the odds 1 through 13. Ooh. I'm thinking maybe not that at the end. Let me back off from that. I know you can do 1, you can do 3, you can do 5, you can do 7. Yeah, you can do 9. Yeah, so I'm sorry. I should have said 1 through 9. Any of the odds 1 through 9 that are in the back of the book you can do. Let me see about the initial value problem. I think you can do, see, we haven't done one, but they didn't show one either, did they? Okay, I think you can do, you can just stop there and we'll pick up the rest of those next time. That won't be any problem. The example 3 is the initial value problem, so we'll hang off of that and come back to it. So, good deal. Any questions? Yeah.
What do we use homogeneous and homogeneous? Don't we have linear, homogeneous functions and homogeneous?
Okay. What we used to call homogeneous were if the differential equation was equal to 0. If it was not equal to 0, it was not homogeneous. So we use that term there for that reason. Now we're using it if all the terms have the same degree. Two different meanings, and I think before they just call it homogeneous equations or homogeneous system. I don't know. I mean, you hate it.
I'm saying in mathematics, I thought we had homogeneous.
Right.
Use that in linear abstract or something like that.
Right.
And then now we're saying homogeneous and we're saying homogeneous. So I'm trying to see which one is which.
I don't even know what the correct pronunciation is. They use the same or different. I don't know. Maybe it's coming up later.
I think it can go either way.
I think you can do it either way.
Yeah, meaning in different.
Yeah, I thought they said.
No, I'm sorry.
Homogeneous is very mapping or something like that.
Okay. I'm sorry. I was jumping backwards, not or ahead or something. When we have, we're going to skip chapter 3 for now. When we get into chapter 4, I'm sorry. I was thinking we had already gotten there. Chapter 3, in chapter 2, what we're calling homogeneous or homogeneous, whichever you want to call it, or when they have the same powers. Okay? In 4.1.2, we're going to talk about homogeneous or homogeneous equations, not necessarily differential equations, but equations. And that means they're equal to 0, not that they have the same power. So a differential equation has a homogeneous differential equation means they all have the same degree.
Which makes sense because
the
prefix
Yeah.
homo is same.
Yeah, same, yeah. But later we're going to say that a homogeneous equation or homogeneous equation is one that's equal to 0. But it won't be a differential, it may be a differential equation, but and I wish, I mean, of all the words in the alphabet, couldn't they come up with a different one? But I don't know why. I do not know why. But these are homogeneous differential equations, if they have the same homogeneous equations, I think is how they say it. But it's still enough to be confusing. But we haven't gotten there yet. I was thinking we had already done some, but we haven't. That's coming up.
Okay, let me go get some more margins.
Okay, right, exactly. Make sure it's pasteurized too. Okay. Take care.